So, in the previous lecture, we have seen about a basic criteria required for sustained oscillation, and in the coming lectures, we'll see about the different type of oscillators. So, in this video lecture, we'll see about the Weinbridge Oscillator, and I'm Dr. Mohan Lakshmi, Professor and Head, Department of ECE from Kanyakumari District, Rohini College of Engineering and Technology. A Weinbridge oscillator, it is a type of phase shift oscillator, so which is based upon a Weinbridge network which comprises of 4 arms connected in a bridge fashion. Here, 2 arms are purely resistive, while the other 2 arms are a combination of resistors and capacitors. In particular, one arm has resistor and capacitor connected in series, say R1 and C1, while the other has it in parallel, which we say, for example, R2 and C2. So this indicates that these 2 arms of the network behave identical to that of a low pass or high pass filter. So which indicates or which replicates the behavior of the circuit shown by the figure given below. So you can see this is a Weinbridge network. One arm it is connected in series. So here, as I told you, so 2 arms will be purely resistive, and the 2 arms will have the combination of resistor and capacitor, and one arm has a series connection, and the other one has a parallel connection of resistor and capacitor. When you have a series connection, then it will behave as an high pass filter. When you have a parallel connection, it will behave like a low pass filter. So in the circuit at high frequencies, the reactance of the capacitors C1 and C2 will be much less, due to which the voltage V0 will become 0 as R2 will be shorted. Next, at low frequencies, the reactance of the capacitors C1 and C2 will also become very high. However, in this case, the output voltage V0 will remain at 0 only, as the capacitor C1 will be acting as an open circuit. So this kind of behavior exhibited by the Weinbridge network makes it a lead-lag circuit in the case of low and high frequencies respectively. So how to calculate the frequency calculation? So amidst of these high and low frequencies, there will be a particular frequency at which the values of the resistance and the capacitive reactance will be equal to each other, so which could generate a maximum output voltage. So obviously we know that this frequency is referred to as a resonant frequency. So a resonant frequency for a Weinbridge oscillator calculated using the following thing. So for example, so it is given here, we know that R1 and R2 is involved, C1 and C2 is involved, and this we denote it as R and C, and of course the resonant frequency is given by 1 by 2 pi RC, that is R1 R2 it is substituted with R, C1 C2 substituted with C. So when it is in the square root, then it becomes so R square C square, so it obviously it becomes 1 by 2 pi RC. Further, at this frequency, the phase shift between the input and the output will become 0, and the magnitude of the output voltage will become equal to 1/3 of the input value. So in addition, it is also seen that Weinbridge will be balanced only at this particular frequency. So in case of Weinbridge oscillator, the Weinbridge network of figure 1 which we have seen will be used in the feedback path. So we have a circuit. In turn, this feedback path will have a Weinbridge network as shown in the below figure, that is in the figure 2. The circuit diagram for Weinbridge oscillator using a BJT is shown here. So you can see a Weinbridge network is connected at the feedback path, which is connected to one output. In these oscillators, the amplifier section will comprise of two-stage amplifier formed by transistors Q1 and Q2, wherein the output of the Q2 is backfed as an input to Q1 via Weinbridge network. So you can see which is shown within the blue color enclosure which is shown here, right? Here, the noise inherent in the circuit will cause a change in the base current of Q1, which will appear at its collector point after being amplified with a phase shift of 180 degree. So this is fed as an input to second transistor Q2 via C4 and gets further amplified and appears with an additional phase shift of 180 degree. So this makes the phase difference of the signal fed back to the Weinbridge network to be 360, satisfying the phase shift criteria to obtain the sustained oscillation. So to obtain the sustained oscillations, you know, either it should be a 0 or 360 degree. However, this condition will be satisfied only in the case of a resonant frequency, due to which the Weinbridge oscillators will be highly selective in terms of frequency, leading to a frequency stabilized design. Thank you.